Thank you, Jello, for your introduction. Good morning. Welcome to another day of IPAM workshop. Today my talk is harnessing mean-field game and data science for mixed traffic. So I actually narrowed down this title a little bit. The one in the website actually is too broad. And this is a joint work with the PhD student Kuan Huang, who's actually has been presenting a poster of part of our work this week, and also Professor Qiang Du from Applied Math and Physics, and Professor Xi Chen from Computer Science. All of them are from Columbia University. First of all, I want to briefly talk about my understanding of the mixed traffic and the state of the arts. So I divide this mixed traffic into 4 phases. From pure human-driven vehicle, so I will call it HV from now on, and all the way to pure AV. Basically, it's a word full of only the autonomous vehicles. So I will use AV for short. And in between, we will have HV dominated and AV dominated phases. On the y-axis, so I use this modeling complexity. So how I define whether a model is more complex than the other. So it depends on how they model the environment, whether there's uncertainty or not, and whether there exists a heterogeneity or not. So I think this one is a very subjective measure, and if you have a question, we can discuss it. So I will start from the pure AV's phase. So in the past few decades, actually, transportation community had developed a large number of models to understand how human drivers drive, or how HV move on the road. So it can be divided at 3 scales: microscopic, macro, and meso. So micro basically is when we model individual cars' movement, and the macro is we instead of model discrete cars, we model a continuum flow. So I think in the tutorial week, both Dan and Ben have introduced some of the models, and the mesoscopy is more focused on model the queuing and also the queue length behavior. And now we move to all the way to the other extreme, which is the pure AV phase. So I basically think that most of the modeling development is focused by the traffic and the control community. So they assume all the AVs are cooperative. Then basically they can model this so-called CACC, the collaborative adaptive cruise control. So basically a platoon of AVs move along the road. And then when we look at this actual mixed traffic phase, and I basically assign this AI and robotic community to this phase, because I think most of the work I have reviewed I've basically published in computer science or AI conferences, and for people either study this how one AV interact with one HV. Usually they basically play a game, either like a differential game or a Stackerberg leader-follower game. And when we increase this, when one AV actually interact with multiple HVs, I use M here. M actually is a large number. Then probably people use reinforcement learning model. Basically, we want to train the driving policy of one AV in an ocean of HVs. And so HVs actually behave like a background traffic. And when we gradually move towards the AV-dominated phase, then we have to understand how a finite number of AVs interact with an ocean of HVs. So I treat this as N AVs plus M HV. So I think AI and the control community try to propose different models in this phase. AVs probably either they use the multi-agent reinforcement learning and they are cooperative, and then they try to learn to improve their driving policies with the background traffic. And the traffic flow community actually proposed another type of model called multi-class traffic flow. So basically, AV and HV are two types of classes, and then they may follow different traffic flow models. And then when we integrate them, we try to understand the stability issues. And then when we move to this AV-dominated phase, so many transportation researchers actually focus on how a finite number of AVs interact with a single HV, because HV we deem their behavior as unstable many times. So their perturbation in the driving behavior can actually disturb the stability of the AV platooning. So that's one, actually is a relatively understudied phase in the existing literature. I think in mixed traffic, we need to understand multiple questions. The first is, how do we develop a scalable AV controller? So this will be also the main focus of my talk. And the second is how humans may gradually adapt their behavior to the increasing number of AVs. So this is I think people are trying to look at this way. I think Katie also provides some comprehensive tutorial on the human factor side. But I think this is an understudied topic. And the last one is how AV actually interact with HV and how we can characterize such interaction and then understand the microscopic aggregate pattern of this interaction. As I mentioned, I will mainly focus on the first question for this talk. And to design AV controller, I think the first question we need to consider is what is an autonomous driving model we want to use? So, or we call it basically AV model. So I add a third axis in this chart, so it may not be easy to see. So it's called vehicle automation. Usually, I think in a pure AV world, so level 1 plus model should be fine. So that's why when people talk about cooperative platooning, so people use like CECC, ACC, or CECC. I think that's okay. But for the mixed traffic phase, I think we really need a level 4 or level 5 automation to deal with this complex situation, especially the irregularity and the randomness of human drivers. So this is, I want to convince you with this message using some video that I will show you soon. So as I mentioned, so when people work on the pure AV world or the platooning, so control agents, basically researchers treat each car as a control agent. So what do I mean by control agent? So here you can see, I just used the car following as a demonstration. So one HV follow another HV, and we try to model how we control the speed of this HV. So we call the VI, the position is XI. And usually people model this as a driving controller as a mapping F, which is parameterized by a set of parameters theta. And the input is, especially in car following model, is the headway, their speed difference, and the current speed of this car I. And then they try to model the acceleration. So the existing models include the CCC models. They are usually can be basically modeled as a linear dynamics. And then also there are a lot of nonlinear car following models that can characterize this F. And some people actually model each car as an optimal control problem, then solve the acceleration using a system optimal control and also model predictive control. So how we move from a pure HV world to a mixed traffic. So for example, we flip this the one HV as an AV. So then basically the main modification is on this the parameters. For example, in terms of reaction time, probably HV has a longer reaction, but AV has a shorter one. And in terms of information, HV usually perceive local information, but AV have global. So in this sense, I assume AV is also both a connected and automated vehicle. So they can access global information. And in terms of driving control, HV may be heterogeneous, but AV is most homogeneous because they are controlled by computers. So this is what I mean by control agents. But my argument is we really need AI agents. I think many of you probably have seen this short video clip. So basically, let me play it. So you know what's going on. Basically, the Waymo car tried to merge to the main line of the highway, but then even all the HVs that were able to do that, including the car which was trying to shoot the video of the Waymo, but Waymo couldn't, so he had to get off the road. So basically, I want to pinpoint two important messages here. If we control AV in the future using just the simple control mechanism, it may not be simple, but like it doesn't understand this human interaction or intention. For example, in this case, we assume, okay, nobody slows down because people are not actually cooperative. They, especially people in California and Arizona, they encounter AV so many times, so they know they are conservative. I think one of the speaker pointed out. So then they just don't want to yield to these AVs so that they can merge in. So another aspect that AV may not be able to capture is they don't have anticipate behavior because they realize, okay, I'm approaching the end. If I don't force in, then I won't be able to get in. Usually human driver adjust their behavior, but apparently this Waymo couldn't. So that's why I think this anticipating or proactive behavior is also important. So that motivated me saying that, okay, we need AI agents. What do we mean by AI agents? So they need to be rational and utility optimizing. And also they either they are cooperative or non-cooperative with the environment. But in this talk, I assume they are non-cooperative agents. And then they should be able to learn and adapt to the environment. And in this mixed traffic environment, AV and HV actually are battling, competing for the road resources. So that's why the game theory, I think, is one of the promising direction to empower driver intelligence. So this is the outline of my talk today. So I will start with the pure AV world, so the simplest, easier one. And I will talk about how we use mean field game to model this pure AV. So then I will move on to the next one, which is the how we make the AV that controlled by mean field game and the HV and understand its stability. Then I will briefly touch on our ongoing work, how we want to develop learning-based driving policies in this mixed AV-HV environment. And then I will touch upon some open questions. Okay, let's look at the first part. So you may ask why we want to look at both the mean field game and also learning-based game. So because for mean field game or any game theory we use so far, they are all prescriptive or normative models. So they describe how AVs are supposed to drive in the environment, and usually they deal with a deterministic environment. So, but we want to model how they actually dynamically interact with each other. So it's more like an evolutionary game, and our interest is the equilibrium. So what the equilibrium look like? So that's why in the first part I will talk about the mean field game-based control and how we understand its stability property. But in the real world, actually, the environment is stochastic and dynamic because of the presence of human drivers and also all other road users. So in this kind of environment, we assume all these cars or agents, they actually play a macro game, and then they need to learn and adapt. So we want to understand their learning process. So that's why in the second part, I will briefly talk about the state of the art of learning-based control and and also what's the gap. Okay, let me move forward to this game-based control. But before I move on, any questions or comments about the mixed traffic I just talked about? Okay, good. So let me give you a setup of how we apply this mean field game to the AV control scenario. So we start with a differential game. So you can see on a ring road, 5 cars are moving, and our goal is to see how we control each car's velocity vi across time. And then we assume each car has an objective function j. So it's composed of 2 parts. The first one, we call it cost function. So we need to integrate over time from 0 to big T. Big T is a pre-specified planning horizon. So this cost function can include the running cost, congestion, or safety or emission, whatever goal you want to put in there. And the big V of T is the terminal cost. And our interest is the Nash equilibrium. So how do we define this equilibrium? Basically, the J of Vi star should be the minimum when others' velocity is held fixed. But then this equation should hold for all the cars. So then we know the Nash equilibrium is reached. And then but the question is, if we increase the number of cars, and we still want to solve the Nash equilibrium for the control for each car, so this becomes not scalable. So mean field game actually can achieve 2 advantages. One is that it can propose some scalable control of many cars, and then we somehow found that there's a link between this mean field game and the existing traffic flow theory. So that's why we call this mean field game theory that in the context of AV control as a new traffic flow theory. So what is a mean field game? So that this is an emerging game theoretic topic to control the multiple agents in a system. It actually mainly focuses on when the number of players go to infinity. So we also can call mean field game as an n-player limit of a dynamic game. Basically the original game is non-cooperative Nash game. And the mean field game, actually, if you look at this 2 reference down below, so it was proposed by a group of engineers and also economists separately, actually in consecutive years. And it was able or successfully explain many phenomena we observe in the real world. The first one is the Mexican wave. The second is the fish schooling. So you can see all these systems actually are comprised of a large number of agents, and they do their distributed movement, but in aggregate, you can see some pattern. I think Benedetto also in last week's Friday tutorial mentioned about he pinpointed multiple dynamic systems to describe animal behavior. Fish schooling, I believe, is one of them. So mean field game can be treated as another alternative to model this kind of behavior. But I think there's one big advantage of mean field game is they actually start from micro behavior and then try to scale up to bridge this macroscopic aggregate behavior of a system. So I will talk about why this is the case later on. In this, let's come back to our context. So when we apply mean field approximation, this is what will happen. So we still have a finite number of cars, and then each car has their objective function. But when we apply this mean field approximation, so the J objective become a we remove all those index. And it's still composed of two parts, cost function and the terminal cost. But instead of looking at the individual cars' velocity control, instead we look at the these new notations. One is the velocity field U of xt, one is the density rho of xt. And to solve this system, we need some initial density rho of x0 and terminal cost for value function, and also boundary conditions. How we solve this or formulate the mean field game, so it's called a forward-backward system. So we start from agent dynamic. Assume each AV react to other cars, and their goal is to solve an optimal control problem to minimize their own objective J, but this objective depends on all other cars' actions. But instead of solving an infinite number of optimal control functions, so we assume these cars are anonymous, and then they have identical objective function. Then we mainly look at a generic car's moment. So this generic car just solve objective J, and you can see all the other cars' velocity actually is reduced to traffic density. So I will skip how this works derivation part, but you just the basic idea is all other cars' velocity actually contribute to the density, and then this car just need to select its velocity in response to the traffic density. And assuming when we solve agent dynamic, the density is known, and then we can solve actually a velocity field. And then we plug in this velocity field to the mass dynamic, which is the flow conservation equation, or we call the continuity equation. Then when we plug U here, we can solve traffic density rho. Then we feed rho back to the agent dynamics. This process just go on and on until an equilibrium is reached. And then the agent dynamic is formulated as a HJB equation. It's solved backwards. And actually, the flow conservation equation, usually in a general mean field game system, is called FPK equation. It's a forward equation. But the difference here is we use the deterministic version of FPK. There's no randomness because cars cannot disappear all of a sudden. So in terms of the flow conservation, it's deterministic. So it's a relatively simpler equation, but actually in terms of properties, it's a little harder to prove. Any questions here? Okay, good. So with this mean field game system, what I want to show is to compare a mean field game we propose with the existing first order traffic flow model, which is the LWR model. And then first demonstrate how this mean field game can actually stabilize the shock wave faster. And then we will actually provide a link between them. So if you remember, the objective function include a cost function. Here, we found out LWR can be reinterpreted as a mean field game using this cost function. So what's the meaning of this cost function? So it means U is the speed, and the big U actually is the fundamental diagram. It's a function of rho, traffic density. UM is the max speed. So we found out in LWR, actually, people's goal is to try to optimize their yield to be as close to the equilibrium speed as possible. So on the top of this, we add another term is they are not only try to match equilibrium speed, they also have try to avoid crowd. So rho j is the jam density. So we just add one extra term to this cost function. And then we plot the equilibrium solution down below to compare them. So let me quickly explain the relation between the top figure and the bottom. So the top one, we start from a discrete curve setup. But then because we apply mean field gain or traffic flow, so that's why what we actually solve is the velocity field and the density field. So it will be the blue and the red line in this figure. And so we will use this color palette as a background to show how the traffic density actually evolves in time and space. You can see we start from the exact position of the cars, and then so here we have a little more cars, so it's more dense. So that's why we have bell-shaped traffic density. And then after you evolve, you can see for LWR model, the shock wave actually appear. So this is this region. So cars are moving slowly, but for mean field gain, actually, it smoothed out to a uniform flow much faster. Oh, do we have some?
Sharon, sorry, interrupt. I think we have a question from Benjamin. I will unmute him.
Okay, can you hear me?
Yeah.
Yeah.
Hi. So about this here, I mean, one thing then when people do classical traffic modeling is they always stress this thing that cars should not be affected by what happens behind them, but only what happens ahead of them, at least for human drivers. And then in the famous D'Aganzo paper and so on, people have fundamentally criticized terms that involve essentially variations in rho in a direct fashion. So the question here with this one, avoid the crowd. So one way to see it is that if cars are more dense ahead of me, I tend to not accelerate them as much, right? Which makes complete sense. But it could also then mean that if cars behind me are very dense, it makes me accelerate more, which one could argue is not necessarily what one should implement in AVs or what human drivers would not do. So the question is this MFG formulation still forward-looking, or is it really sort of forward and backward-looking, meaning that if cars are behind me are very dense, I would as a consequence accelerate more to get away from them?
So yeah, this is a good question. Here, actually, even mean field gain, they mainly use their local density to determine their speed. However, they are forward-looking in terms of time, not space. So basically, their current speed actually is determined by all the density rho from the current time t to all the way to big T.
So does that mean that if I construct an initial condition where the density behind me is much, much higher, would that contribute to higher, like me getting faster, or would I not get faster in this setup then?
So in ring road, that may be a factor. But in say infinite long road, so the traffic behind won't influence its behavior for sure.
Oh, I see. So the avoid crowd is really forward looking. There's an intrinsic asymmetry in these MFGs because you look forward in time.
Yeah, exactly. Forward in time, but not in space.
Right, but looking forward in time, because cars move forward, has some implication on essentially more looking forward in space as well, would it not?
Yeah, on ring road, yes.
Okay, thank you.
Yeah. Thank you.
Thank you, Sharon.
Thanks, Yellow. So yeah, here I want to demonstrate that basically the AV controlled by mean field gain actually can basically they anticipate this jam actually, as Ben asked, because these cars before they enter the jam, they can anticipate this jam. So that's why they already decelerate before they enter. But if it's LWR, because their speed is just controlled by the current rho at this location. So when this green car is here, he doesn't know there's a jam in front, so he just still drive at a normal speed. And probably if I show the fundamental diagram, it's more clear. So the green dotted line actually is the green shield, blue dotted line is the green shield fundamental diagram with the density and the flow. And the black dotted black dots are the we fix some locations, assume we have some virtual loop detector, and we measure the flow and the density. So these black dots are from the mean field game. Actually, if you connect all these dots for one car, you will see our fundamental diagram is flower-like. So if the car traffic state start from, say, outside here, they will eventually converge to the green dotted line, which the blue dotted line, which is the green shields. So that shows that actually there exists a more complex mapping between rho and U if we solve mean field game. So it's hard to see, to use one like a clean fundamental diagram to describe the mapping between rho and U at the current time and the current location. But yeah, we haven't been able to understand this mapping very well, the mathematical and also mathematical property. But we do find out that there's this kind of link between LWR and mean field game. First of all, LWR is a mean field game with cost function that will drive car's speed towards equilibrium speed. I think this is also proved by many researchers. For example, I think in Dan and Ben's experiments, actually try to control AVs towards to match the speed in the neighborhood or with the equilibrium speed. I think that actually kind of is also LWR's behavior. But correct me if I'm wrong. Second, we found out actually LWR is a myopic mean field game. So that means they only look at the current times density and then make their speed choice. They don't look forward in time. So that's why it can have this kind of, it doesn't anticipate. That's the key difference between LWR and some other specially designed mean field game. Okay, so this is the pure AV control. I will move on to how we show the stability analysis. So basically, up to this point, I talk about how we control AVs in a world that's full of AVs. But if there's some HV traffic is blended, so how this stability works. So the stability of the mixed traffic in this mean field context is defined from microscopic traffic flow perspective. So it's not from the car following perspective. So the definition is, first we define uniform flow, and we have a equilibrium density for AV and HV, and we assume at the uniform flow, AV and HV share the same speed. The stability conditions, if we perturb the initial density, then the density, velocity and density profile, as time evolves, won't basically increase this magnitude of the perturbation. So we call it linear stability condition. And so in this work, we showed what's the critical AV penetration rate to actually stabilize the traffic. Actually, it's much higher than what many people have found so far because of the different model we use. And then we found out actually mean field game by design can be inherently basically stabilize the traffic. We don't have to specifically basically find the stability conditions. So this is how we control AV using the mean field game we proposed. And we use ARZ model, which is second order traffic flow model, to control HV. And then these are the parameters, the variables of interest. So they share the same flow conservation equation. So each type of class vehicle actually follow this, has conserved density, and their total is called rho total. And for mean field game, we need to solve the dynamical HJB equation. So here we add this beta parameter. So it's a sensitivity parameter in response to the HV density. And ARZ is the momentum equation we use here. So the reason we pick the second order because we need HV to generate stop and go wave so that we can use AV to stabilize this kind of this stop and go wave. But LWR, because it's first order, so it will never generate a stop and go wave. And then we run the experiment. So here we plot a stable and unstable region. So the x-axis is the AV penetration rate of increase from 0 to 1, and the y-axis is normalized the total density. So the blue dot is.
Sorry to interrupt, Sharon. We have 5 more minutes.
Oh, okay. Thank you. So the blue dots are the stable region, but the red cross is the unstable regions. So I just pick one. So when the total density is 0.4, so you can see if we don't add any AV. So this, we plotted the density wave as time evolves. You can see eventually this shock phase stop and go waves is formed. But if we add 30% of the AV, so basically it's some point here, so it actually stabilizes the traffic. So you can see for rho, when rho is equal to 0.4, we need at least 20% of the AV to stabilize the traffic. I think it's definitely debatable because if we use different model, we will end up with a different penetration rate. And we also test how this beta reacts, how sensitive it is to stabilize the traffic. I think Ben has a question.
I wanted to very quickly check in just to make sure I understand the mechanism, right? So it seems to me that based on the equation on the prior slide, the ARZ, the only way the AVs affect the human-controlled vehicles is by the density, right? By affecting the density whereas on real road, you could have an AV, for example, that drives more steadily and the vehicle behind it cannot overtake because traffic is very dense and therefore makes it more regular. But this is not what's happening here, right? It's more that the macroscopic density effect, they relocate along the road and therefore stabilize the flow. Do I understand that correctly?
Yeah. So this is the problem for microscopic because we cannot model this overtaking behavior. Mm-hmm. So yeah, for multi-class, I think we are also struggling with this. So when we put the two types of class of vehicle together, if they have different speed or different acceleration, so we cannot model this one car block the road and then.
Right. But I think you still need some level of overtaking because you allow the AVs to choose a different speed than the human-controlled vehicles, right? So that, in a sense, requires that you have some level to overtake, because otherwise you can never go faster than the traffic flow if you're single lane, and if you go slower, then obviously you would hold back all the vehicles. But here it looks like vehicles have the possibility to go around each other in some way. Isn't that the case?
Yeah, I think we assume they only have the same speed at the equilibrium, the uniform flow state, mm-hmm. But in transition phase, they do have different speed. So they can overtake each other.
They can go around, right? Okay, good. So it's really purely macroscopic. The AVs can choose to go in different places, and then they do it for overall stabilizing the flow.
Yeah, exactly.
Okay, great. Thank you.
Yeah, thank you for pinpointing that. So I think one thing we want to consider is if we use multi-class model in the future to model AV-HV interaction, so how we can actually model this kind of overtaking or non-overtaking behavior. I think that's one direction to go. Okay, we don't have too much time, so I will quickly talk about this, my thoughts and the gaps I identify in this, how we use reinforcement learning to control, to train the driving policies. Because I think this is a famous quote, it's not the strongest, that's why it's the one that most adaptable to changes. So I will skip this, but what I want to identify is if in a mixed traffic environment we want to control AV. So there's one challenge is how we model the mixed traffic environment, because that simulation environment is the key for the reinforcement learning, the training part. So basically it's called the imitation learning on mixed traffic. I don't want to talk about how we imitate the HVs, but how AVs works here. So I use the basic Waymo level 4 data set. They have this camera image and light up on the cloud. So we just train a very simple LSTM model to basically capture how Waymo actually drives using a behavior cloning approach. So the blue box is the ground truth, and the orange one is what we predict using LSTM model, and the red car is this one in front. So basically, we try to model its car following behavior, and we use some baseline to compare, and then I will skip the detail of LSTM model. What I want to say, because the key of modeling the mixed traffic in the future actually is the data. Because the Waymo data, so far is the only L4 driving data. Probably Toyota or other have more, but I'm not aware of that at that time. But I think using some real AV data to train their driving policy and then incorporate it into our mixed traffic environment is a very important, crucial step to train the future AV driving behavior. Another direction is if we add more and more AVs, we need to control all of them using multi-agent reinforcement learning. So another challenge is how we can move from single agent reinforcement to multi-agent. And because they are not, the environment is not Markovian anymore. So that's why actually now there's a emerging trend of study that you basically at the intersection of game theory and multi-agent reinforcement learning. And then I quickly classified the existing AV control model and mapped it to this chart. So you can see, I think the Professor Alex Beijing group and KC Wu, so basically have a bunch of papers, but their AV control for multiple AVs mainly focus on they share the global information and all the cars cooperate. But how about the cars share the common information, but they are competitive? So my argument is why they may be more competitive than cooperative, because in the future, each AV's goal is to move their own occupant from A to B at the shortest path. It's not if they cooperate, actually their driving time may get worse. So that's why how this non-cooperative game training policy may work here. Also, if they don't even have global information, they are not connected, they are independent learners, and they are cooperative, how we train the policy. I think these are all questions that are unsolved. Okay, let's come back. So I will skip the summary, but I want to raise some open questions when we develop this scalable AV controller. So one is the autonomous driving model. So what model we want to use? So here we use a new model based on mean-field gain control, but there are many existing physics-based model and also the machine learning-based model. So which one we should pick? And then how we can bridge the multi-scale from micro to macroscopic. So if we model microscopic interaction between AV and HV, how we can scale it up to macroscopic level. And then how do we build a mixed traffic simulator? So as I mentioned, we may not have a lot of data to train those driving policies. So can we utilize some open data that is published for different purposes for our driving policy training? And also the social implication. I think many speakers also mentioned like legal or this bias or fairness issues. And there are some other issues. I suggest you to check out this paper, Machine Behavior in Nature. So they talk about how human behavior may adapt to the presence of the more and more machines around the humans, and also how we actually model this interaction. As Dan pointed out, if we use a macroscope model, we cannot actually understand how they overtake, whether they overtake or whether they have lynching behavior. So how we can model that, but also have a more scalable model, I think it's also another question. Yeah, that's all about my talk. Thank you very much.